In this video, we will learn about friction. We will look at the cause of friction, the equations governing friction, and we will also solve a problem related to friction. We will also discuss the two different types of friction, one of which is known as the static friction and the other one as kinetic friction. We will also look at how frictional force changes as we change our applied force. We will also look at the domains in which static friction works and the areas in which kinetic friction operates. In order to do that, let's take a simple example. We take an object and we place it on a rough surface. Now let's apply a gentle force on this box. If we do that, we realize that this object doesn't move. But how is this possible? That we apply a force and the object does not move. In fact, if we use Newton's second law of motion, F equals ma, we clearly see that there is a force, therefore there must be an acceleration. So what's the way out of this? The way out is that there must be another force applied on this box, which is preventing the box from moving. And now if we use Newton's second law, we realize that F is 0. If the applied force is 0, the acceleration must be 0 as well. This force which was preventing the motion is what's known as frictional force, or in short, just friction. So we can summarize friction as the force which resists the motion. The force in the red is trying to stop this object from moving. It's resisting its motion, therefore it's known as the frictional force. In this example, the frictional force is enough to prevent the slipping of this object. This type of a frictional force is known as static friction. We can say static friction is a friction when surfaces do not slip past one another. Furthermore, since this object is at rest and is not accelerating, we can write this equation. This just says that the applied force is balanced by the static friction. Now let's try and increase the amount of applied force. If we increase the applied force, we may still find that the object doesn't move. If the object doesn't move, the only way is that the frictional force must have increased as well. Now the frictional force is once again balancing the applied force. And we can once again write the same equation. Now let's increase the applied force even more, such that the object is still at rest, but it's on the verge of motion. If we increase the force by a small amount, the object will begin to slip. Since this object is still at rest, it's balanced by the frictional force. The frictional force must have increased by the same amount to balance the increase in the applied force. We have the equation of balance, that is, the applied force is balanced by the frictional force. The magnitude of friction when the object is at the verge of slipping is the maximum value that the static friction can have. This is known as the maximum static friction. But what's the cause of friction? To answer that question, let's zoom into the surfaces. We find out that these surfaces are not smooth, although they appear to be. And there are particular spots where the two surfaces are in contact with one another. It's at these spots that cold wells are formed. That is, the two objects get bonded together. The cold wells resist the motion of the object. This is the explanation for friction. If we plot a graph between the applied and frictional force, we realize that as we increase the applied force, the frictional force also increases. But this happens until we reach the maximum static friction. That is the frictional value up until the object stays at rest. Fortunately, we have an equation for the maximum static friction. The equation for the maximum static friction is Fs max equals mu s times force normal. Mu s is known as the coefficient of static friction, and it represents the roughness of the two surfaces in contact. Fn, on the other hand, is the normal force or normal reaction. In our case, Fn is the force which balances the weight. So far we have been in the domain of static friction, that is, the object is at rest. Now let's increase the force by such an amount that the object is forced to move. The object slips forward and comes to rest. Friction is the force that's slowing this object down until it comes to a halt. This friction is kinetic friction. It's different from static friction in that static friction acts when the object is at rest, while as kinetic friction is present when an object slips. So we can define kinetic friction as a frictional force that resists motion when objects are slipping. We have a nice equation for kinetic friction, that is Fk equals mu k times force normal. Mu k is the coefficient of kinetic friction, and it tells us how rough these surfaces are. If the surfaces are really rough, mu k is going to increase. On the other hand, if they are very smooth, then mu k will be smaller. Fn, on the other hand, is just the force normal. In almost all cases, the coefficient of kinetic friction is less than the coefficient of static friction. This directly implies that kinetic frictional force is less than the maximum static frictional force. Now if we plot a graph between the applied and the frictional force, first of all we get a linear relationship between the applied and frictional force until we reach the maximum value of static friction. If we increase our force further than that, now we enter the domain of kinetic friction. Since kinetic friction is less than the maximum value of static friction, we get a line which is lower than the maximum static friction. Let's look at an example here that helps us understand friction. So here's a ramp which is rough, and we place an object on this ramp. We realize that this object stays at rest. Weight, which is pulling the object down, the normal force, which is perpendicular to the ramp. There's a third force that's pointing upwards. That's the force of friction. In this case, it's the static friction that's preventing this duck from slipping down the slope. We want to write some equations that relate force of friction with force of normal with the weight of the duck. Let's draw all three of the forces present on this object. Let's assume that the angle of the ramp is theta. Then the angle of the weight with a line that's perpendicular to the ramp is theta as well. We can split the weight into two components, one perpendicular to the ramp, which is given as W cosine theta, and the other component parallel to the ramp, given as W sine theta. Since there is no motion perpendicular to the ramp, we can say that Fn should be balanced by W cos theta. Furthermore, the duck doesn't slip down the ramp, therefore we should write that the force of friction should be balanced by W sine theta. If we divide these two equations, we get force of friction over force of normal equals tan of theta. I hope this video was helpful. I'll see you in the next one. Take care and keep learning.